Yeah, so today we're just going to be reviewing for your exam on Wednesday. So I'm just going to pop us into immediately some review questions. We ended really fast on this topic, so we're going to start out with some of the modulation happening at the synapses. So then it's going to be some grab bag questions, and as this raises points of confusion for you, jot those down so we can have some time for questions as well. Hopefully this method directly from the website will work, because it wouldn't let me insert these slides this morning as I usually do. Is it letting you go? Oh, it's showing what people are voting for. Okay. I guess that's how we're doing it. I know at least one person has gotten it. I'd like to see it count ideally. So seeing no other answers, this is true. So C and E firing together means what we have here at E is a modulating neuron. So it's increasing the activity of C. So when it acts on C has a certain amount of neurotransmitter that it releases on its own. But when E fires with it, it causes C to release extra neurotransmitter. So this is a way that we can potentially increase the likelihood that X will fire off on its own. Let's see if there's a way I can get the usual counted form. Turn this off for a second. Doing it again. All right. I'm just going to time these, so just showing your answers as they come in. I'll just say, be brave. If you don't have the same answer as the first person, that's totally all right. I want you to, for all of these, I'd like you to choose as many as you can. Okay, great. So yes, what this modulator neuron E acting on C is doing is facilitating its activity. So this is presynaptic facilitation, where we have this axonic connection. Okay. So now we're going to try a different modulating neuron. In this case, which is the the least likely to cause an action potential to fire in our postsynaptic cell. Okay. So what we have happening here is that G and F each release neurotransmitters that, because we're green, are going to assume that they cause excitation in our postsynaptic cell. So if either G or F fires alone, they'll cause a graded potential, probably a slight depolarization, right? They're excitatory, which may or may not be big enough for an action potential. If G and F fire together, we would have to add up those graded potentials, since they would both likely be depolarization. They might cause an action potential. But when we have this modulator neuron H, if it fires at the same time as F, that's going to suppress F from firing. So we add up graded potentials and we can kind of think of this H as, we want to think about H as suppressing F. So F likely wouldn't release neurotransmitters, so we would have F and H as our least likely to cause an action potential combination. This is the same picture, but now we want to know what neurons firing together might be enough to cause an action potential. Okay, go ahead and get your answers in. Put them in. No. Okay. Take a look. Okay. So the majority of you got this right. Yeah, so G and F are both excitatory. So if they fire together and H isn't firing, isn't inhibiting F, then they might add up to create an action potential. Okay. So what is the name or what's going on in this image? Oh, okay. There we go. Thank you. How about now? Okay, great. See what we got. Great. Yeah, this is an example of pre-synaptic inhibition. So we're talking about before the synapse, pre-synaptic. Because we have H suppressing F, that is inhibition. The fact that G and F both act on Y, that could be an example of our term convergence, that neurons can converge on a single postsynaptic neuron. To make a question about that, but it's kind of an example here. Those might be all the questions in here I put on modulation. Any remaining questions about this? So we could have more complex system, right? We could have like 5 different presynaptic neurons converging and multiple modulators either inhibiting or facilitating. But this is just the basics of what we should be looking for. So does it upregulate or inhibit?
Is there any other indication whether that's in the inhibition other than the color?
I might tell you that it does inhibition depending on the example. For this, it's the color. The other thing we can see is this image next to it. You'll notice it's showing you that less neurotransmitter is released when the 2 are firing together. So that arrow there, this is trying to tell you that if F fires alone, it's the switch neurotransmitter. And the fact that there are 2 arrows here are trying to tell you that they're both firing. Okay. In that case, other questions. Great. So here we have one from a while back, thinking about our different types of membrane proteins, channels or pumps, that good stuff. Which one is maintaining our concentrations of sodium and potassium? Okay. Yeah, the answer is the sodium potassium pump. So when we're thinking about physiologically normal concentrations, what we're saying is what's helping us get to our resting membrane potential, because we know that sodium, to get the resting membrane potential to -70, a little bit of sodium comes in and a lot of potassium goes out. But if that's happening all the time, we would expect our concentrations outside and inside the cell to change, which would mess with stuff. So the sodium potassium pump is the reason that we're able to maintain those concentration gradients. So we have that chemical driving force staying pretty much the same when we're at rest. So the sodium leak channels do participate in creating that -70 resting membrane potential. It's really more the fact that we have a lot of potassium leak channels, I would say, is why it's so low. If it was all due to sodium leak channels, we'd have a higher resting membrane potential. And our voltage gated sodium and potassium channels are involved in our action potential. So they're not due to that. They're not describing a physiologically normal concentration, so just like the baseline kind of concentration along the cell. They're specifically involved with firing and then returning to normal. All right, osmosis will also be on this exam. So let's practice an osmosis question again. when we're going from our concentration in moles to milliosmoles, and we're going to assume all these examples will be in a liter of water. I'm going to multiply by 1,000. 1,000 times 0.15 gets us to 150. Usually our examples are kind of in this range because we know kind of our baseline usually is 300 in our cell. That's our typical osmolarity of a cell. So this is kind of the range you would be expecting. Like you should know how to convert between osmoles and milliosmoles, but if you're second guessing yourself, good place to be. Maybe I will make this one bigger just so you can read. A little. We got some nice long explanations. I want you to look between time points C and D. Tell me what's going on there. Good. Great. Okay. Yeah, so it's repolarization. So knowing that didn't help us any, these all described repolarization. But when we look at our permeability lines, we can see what's going on. So our permeability of sodium has gone down. So that's the closure of the sodium channels part. And our permeability of potassium has gone up. And that's the opening of the potassium channels part. Those are the two things that characterize the repolarization case. Okay. Think about our phases, think about permeability a little more. Great, yes. The whole deal with the depolarization, the reason we're depolarizing is because we are very permeable to sodium due to the opening of those voltage-gated sodium channels. Next graph again. So now we're thinking between B and C. What we want to know is the inactivation gate first, the activation gate second, and the potassium gate third, the order. Great. Okay. So the majority of you got this one right as well. So During depolarization, which is what's happening between B and C, we have both the two gates of our sodium channel open. For sodium to go through, both have to be open. So our sodium inactivation gate and the sodium activation gate are open. But the potassium isn't coming in yet, so the voltage-gated potassium channel is closed. It only has one gate, which is why we're only describing the one state it could possibly be in. Now let's move between C and E. I meant between C and D. Sorry, guys. So between C and D, let's think about the state. It looks like those of you who picked A just weren't sure which gate was causing those sodium channels to close, but it looks like everybody knew that what's going on is the sodium channels closing. The reason those sodium channels are closing is because the inactivation gate has swung closed. So during this, most of the repolarization phase, this is why we're in our absolute refractory period, because we've closed that inactivation gate. Our activation gate is still open, but it doesn't matter because we have to get through both doors for a sodium ion. And our permeability to potassium has increased because that potassium gate is open. Got some more osmosis. While you're doing this one, I want you to think about whether this is describing tonicity or osmolarity. I think you guys are right, actually. This is tagged wrong. Yeah. Okay. So yeah, water is moving from A towards B, so towards the more solute here. Okay. So is this talking about tonicity or osmolarity, this non-permeating part? Do you remember the difference between those words? Yeah, exactly. Non-permeating means it's tonicity. Yeah. So our trigger for releasing neurotransmitters, that is calcium. So calcium, like sodium, wants to come into cells. So when the action potential, which is that wave of depolarization, reaches the axon terminal, opens up a voltage-gated calcium channel, calcium comes in. It basically is kind of binding onto those vesicles, telling them to bind onto the membrane and release neurotransmitter into the synaptic clot. Just for a refresher on the chloride ions. So the chloride ions, the only place we really talk about them is when we're thinking about the receptors on the postsynaptic cell. So potentially an ionotropic receptor, potentially a metabotropic receptor. But basically, we have chloride ions come into a cell, causing inhibition in the postsynaptic cell, or we might have chloride kind of stabilize the postsynaptic cell, making it harder for sodium ions to come in and depolarize. So it would also count as inhibition. And that isn't paired with ionotropic or metabotropic. It's just one of the type of ion channels that could end up open eventually. More things about the gate and the action potential. Okay, take another couple seconds. Okay, yeah, the sodium inactivation. So we're in this after hyperpolarization. So the sodium inactivation gate is going back to its resting state, so it's opening. But sodium still isn't able to get through, so we know the sodium activation gate must have closed, right? Then our potassium gate is slowly closing, having been open, causing us to go down below -7. Okay, widespread of answers here. So first part, we're thinking about potassium leaving a cell. So potassium leaving a cell, because potassium is positively charged, when our positive charges leave a cell, it becomes more negative. So that's the first part. So that gives us two choices, right? These B and C both have a negative cell. Any questions about that first cell? Like, if that's still giving you trouble, go ahead and straight up memorize it, because it's really important to know that potassium leaving makes cells negative, right? That's a key part of our action potential as well. And as stated here, it's also going to be key to figuring out whether we're having an excitatory or an inhibitory postsynaptic potential. So when we're deciding between EPSP and IPSP, they stand for excitatory and inhibitory postsynaptic potentials, respectively. So all we're trying to figure out is, excited, are we more likely to fire? Inhibited, are we less likely to fire? And you pretty much can directly just associate negative with inhibitory, right? Because we have that threshold of negative 55 that we have to reach to fire off the action potential. And negative 55 is a negative number, but it's more positive than negative 7. So when we make the cell more negative, that's an IPSP if we're talking about a postsynaptic cell. Questions on that part? So like if a neurotransmitter bound into an ionotropic or metabotropic receptor, and the result was that it opened a potassium channel, that's how we would flow through our thinking to get to the fact that that would be an IPSP. So we want to think about that with the opposite when we're thinking about sodium, for example. Our answer here is repolarization. So permeability of the plasma membrane means how easy can something get through it. So we're trying to figure out when it is easier for potassium to go through the membrane. That's during repolarization, which is why we are going down on the graph, right? That's why our cell is getting more negative, because when the plasma membrane is permeable to potassium, more potassium leaves the cell. And as we just saw in the previous question, potassium leaving a cell makes it more negative, which is why we're going down. So that's during the repolarization phase. As when it's increasing and the most permeable, but we do want to remember that in general, the cell is more permeable to potassium in the first place with those leak channels, which is why we're at negative 70 instead of like positive 30 or 0 or something with our resting membrane potential. And our after hyperpolarization is not when we are increasing the permeability of potassium, but it is also due to the fact that the membrane is still letting kind of extra potassium flow out. Okay, got this graph again. Great. Now we're talking depolarization because sodium is coming in, because those voltage gated sodium channels have been triggered to open by reaching the threshold of -55. And this is a regenerative mechanism. We have lots more sodium channels opening every time we have a sodium channel open, because it makes neighboring regions more likely to reach threshold, which is basically how our propagation down the axon works. Seen as many as 9, so I assume that's 9 people and not 2 people voting twice. We do seem to pause at 7 a lot, so maybe some of you are voting twice, I don't know. Great. So it's about the calcium. Yeah. So neurotransmitter crossing the synaptic cleft and binding to the receptor, that doesn't take much time. That synaptic cleft is quite small. So it's about those voltage gated calcium channels. They take a little while to open, which shouldn't be terribly surprising, because you remember that part of the way that the action potential works is because we have those delays of the effect of that depolarization on our inactivation gate and the delayed effect on the voltage gated potassium channels. So that's kind of just a feature of voltage gated channels, that they often have a little bit of a delay before they respond. It should be these first two, both A and B. So when the potassium electrochemical gradient is 0, by definition, that means that the chemical and electrical gradients are equal but opposite in magnitude and direction. And it's the electrochemical driving force that tells potassium to move, the electrochemical driving force that tells any ion to move. So those are the two times when we wouldn't expect to have potassium moving through those leak channels. You would always have potassium wanting to move through the leak channels if the membrane potential was positive. The only kind of exception here, since I just said negative, you wouldn't expect potassium to move, or you would expect potassium to move through the leak channels, but if it was past its equilibrium potential of -94, then no. I just wanted there to be more answer choices. Because I know when I give you an either or something in class and then you end up with like A through E on your exam. Different, more intimidating. I don't think I really made that question intimidating particularly, but I tried to make it a little more representative. Fast. Okay. So it is 300. And the reason it's 300 is everyone got the multiply by 1,000 and, you know, kind of do a gut check that it's in a reasonable range if you're not sure. But because here we have a salt, ionically bound molecules, they're going to separate in water, which means we have to do 150 for each potassium and chloride. Means we put all that stuff together, think about the sucrose and our salt, potassium chloride. Okay, great, 450. Yep. Yep. So facilitation is release increases, inhibition would be release decreases. Okay, so I know we're at time, so I'm just going to ask you guys a question before I do something. I realized we didn't do the different receptor types, and we also didn't talk about propagation in these practice questions. If I made like a practice quiz for you guys to do on those for the exam, would you do it? Just raise your hand if you would do it. Okay, in that case, I'll write one so that you guys can practice